Yeah. Wait.
Because right now we're making no stays.
Oh, I see.
All right, welcome back to CS160, everyone. This is a brief reminder that your pilot usability study is due next week, and that for that purpose, you should be both refining your implementation as well as then testing it, right? So keep working on the implementation throughout from now till the final presentations. Also a reminder that today at midnight, your second team evaluation is due, and there's an online form linked from the wiki to do that. All right, let's just jump right in for today. So today we're going to compress the whole history of user interfaces in computer science into one lecture. And we're going to start way in the early beginnings and then slowly work our way forward. All right. Before there were computers, there were other physical interfaces that people used to perform computation. And one of the really interesting ones is the astrolabe. That was used in the Middle Ages to tell the time. And you would find out what the time of day is by a simple observation of either the sun or a known star. And it took into account the season and the latitude of your observation. So think of trying to compute the time just from a position of a known object in the heavens. That's kind of a difficult computation to do, but it was made easier by just very clever layout of different moving parts. So I thought I'd show you. So you may think that, compared to just wearing a watch, this is a somewhat cumbersome method of telling the time. But in the absence of any other alternative, it was quite revolutionary. Moving ahead, with the Industrial Revolution came other ways of mechanical automation. And so prime examples are the jacquard looms, right, weaving machines that would take these string cardboard pattern cards, and they would just sense whether there was a hole or no hole. And that would determine the pattern of the fabric that was woven. Right around the same time, Charles Babbage worked on his, well, same century at least, Charles Babbage worked on his difference engine, which was the first, at least theoretical, working model of a general purpose computer, except it actually never worked during his time. So people afterwards took the plans and then reassembled and built a difference engine that worked. Well, what was, though, the first real success of computing were Hollerith's punch cards. And these came about for the US Census. So every 10 years, the government counts all the people in the US. And in 1880, the census took 5 years to collect the data, and then another 4 years to process the data afterwards. Everything was written down on paper. So clearly, a prime opportunity for automation. You may wonder that maybe what we have enshrined is a census every 10 years because people just had the expectation that that's how long one cycle through the process would take. So just 10 years later, in 1890, there were 16 million additional people living in the US, but the process took 4 years less. It was 4 years faster. Partially because Hollerith sold to the US government these punch card machines where there was a way to produce punch cards from a keyboard, and then you would feed a stack of punch cards into an automatic addition machine that would process them one by one and then just tally the results. So Hollerith was also an entrepreneur. Anyone know what he was up to afterwards, or what punch cards were the foundation for? Small company called International Business Machines, or IBM. And what I thought was just a really neat detail of how did you read these punch cards? Well, actually, there were these cups filled with mercury. You put a card over, and then there were spring-loaded pins from the top. And either the pins were dropped through the holes into the mercury bath, and they closed an electrical connection, or they were blocked by the cardboard, and the circuit remained open. One of the next big advances that came 2 or 3 decades later was the teletype, which was a way to send point-to-point text messages using a keyboard rather than the telegraph and using Morse code. So here you still had to have a point-to-point connection, and you would open and close a loop, but you now had some way of turning characters, for example, ASCII text, and code them into some protocol that you sent over the wire that on the other side was then decoded and drove basically a typewriter. So if you haven't seen one of these before, oh no, I closed the link. Let's open it again. As you can tell, these machines were loud. So what's actually happening is, so there's a full mechanical typewriter that moves across the page, and then based on a decoding of, I believe, 5 bits of the current signal, one of the keys of the typewriter became movable and was pressed into the page. Kind of a marvel of mechanical engineering. The standard speed here was 45 baud. Who remembers accessing the web through a modem ever? A couple people? Okay, how fast was your modem?
28K.
28K, that's about where modems stopped. They actually started around 300 with acoustic couplers, and so this is yet an order of magnitude slower. So it's about 20 milliseconds for each single bit in the teletype. Oftentimes, it was then also, it would print out, but also feed you this 5-bit paper strip. And actually, the teletype is the origin of the word newsflash. So what was a newsflash? Well, there's a special bell character in this alphabet that would either, ring a bell or flash a light. And one agreed upon convention was that, really important news would have 10 flash characters in a row to alert the operator over the noise of the thing just running that something really important was happening and they should pay attention. All right, let's look at some early visions of computing. So ENIAC is widely hailed as being the first all-electronic computer. I went to the University of Pennsylvania undergrad, so ENIAC was actually sitting right around the corner from my undergrad lab. Why did I bring it up? Well, this was ENIAC's user interface. So you had to operate this switchboard in the front, and that was how all programs were entered. Just a year later, at Harvard, another very early system, the Mark I, now had a tape reader. And that doesn't seem like much, but it now combined the teletype with an early computer, and now you could actually type programs in onto tape, and then you would feed the tape to the machine. So this machine was electromechanical. There were no microprocessors around, so it was all built on physical switches and paper tape. And so early uses were for mostly military, so ballistics calculations and general arithmetic. Took about 3 seconds to do a multiplication. Now, one of the pioneers of user interface design for programmers was Admiral Grace Murray Hopper. She was one of the first programmers of the Harvard Mark I. And she developed the first compiler for a programming language. And the whole new idea was that you could have an independent programming language that was independent from the hardware of the machine to describe what you wanted to have done. And that would then get translated into machine instructions, but it might also be portable from one machine to the other. And so really, what are programming languages other than the user interfaces for programmers to communicate with machines? So her work led to the development of COBOL, and she's also credited with popularizing the term debugging and for finding the first bug, which looked like this. It was an actual insect that had gotten stuck in one of the electromechanical switches and prevented the switch from performing. One of the visionaries of this time was Vannevar Bush. So he was a faculty member at MIT, and we're right now in World War II. And he was one of the people who coordinated the effort of thousands of US scientists towards contributing towards the war. And one of the main questions was, after World War II was over, well, what's the role of science now in a peaceful world? And he basically proposed to have this social contract where the federal government funds universities, the universities do basic research, and there's the expectation that eventually basic research then helps both the economy and national defense. And prior to him, most research at universities was actually funded by private corporations. And there was a real sea change that basically his advocacy led to the establishment of the National Science Foundation, which is the single biggest funder of graduate research at American universities today, including, of course, in computer science. So many of the research projects that go on in this building are funded by the National Science Foundation. One thing Bush is especially famous for is an article called As We May Think, which he published in the Atlantic Monthly in 1945. And he starts off, talking about, well, what should scientists do now that the war is over? And really what he lays out is a vision for what computing in general should be about and what the user interfaces for it will look like. So things he imagined was ubiquitous cameras that scientists use during experiments to record all of their observations. His particular embodiment was this camera you wore on your forehead. That didn't come to pass, but certainly we're using billions and billions of images today. He also imagined having the Encyclopedia Britannica, which at that time was the canonical record of knowledge, available for the price of a nickel. He imagined having automatic speech recording, and then the idea he's most famous for is the memex, which is a way of, once you record all of this information, images, speech, notes, how do you access it? Well, the memex in his vision was this desk where you sit down, and the desk has displays that let you pull up an article, and then this article would have trails, and these trails would lead you from one article to a related article, and then that related article would have other trails. So basically this is a vision of hypertext and the web in the technologies of 1945. So what didn't come to pass was this is not all done in microfiche and miniaturized photographs. But what did come to pass was this whole idea of having associations and indexing between lots of different documents for the goal, with the goal of making it easier to access, sift through, find relevant information in large collections of information. So this was a vision piece, and he couldn't actually build the memex. Right? He just speculated, here are the technologies we have, here's what may become feasible. Let's build towards that. Now, no one actually had a really reliable running computer that was easily accessible for quite another while. So the real first set of visionary demos came in the 1960s. So just a little bit of context of what happened in the 60s. The 60s saw widespread availability of transistors, which at the time were thought of as better versions of vacuum tubes. And where were they mainly used? Well, they were mainly used in the national telephone system. So at the point, the most complex technological system that anyone had built was Bell, and it was the national phone system. And so for operating all their local switching stations, that required lots of vacuum tubes. They were expensive, unreliable. That led to the research that led to the discovery of and the development of transistors. So these became available in small quantities. And now if you look at a current chip, so if you may have a Core 7 in your laptop that has about 700 million transistors just in the CPU. And if you look at server CPUs, you're probably at 2 to 3 billion transistors now. Other things that happened in the late 50s and 60s was the foundation of ARPA, the Advanced Research Projects Agency, which was founded to do advanced research, usually with military purposes. But they really were funded right after Sputnik, where there was this moment that, damn, Russia may be ahead of us technologically, so we better pour more resources into our own research. And of course, ARPA and its follow-on organization DARPA then led to the funding of the first networking systems, which led to the internet. What kind of computers did people have? Well, largely these time-sharing systems where you may have a local keyboard and display, but really all of the computation happens somewhere in a basement on a room-sized machine. Now, against that background, one of the really pioneers of human-computer interaction was Ivan Sutherland, who was a pioneer of both computer graphics and human-computer interaction. He won the Turing Award in '88. He was actually a visiting professor here from 2005 through 2008. His name may still be on some door in Soda Hall. And he was also at Sun and is generally around Silicon Valley. What he's known for is an application called Sketchpad, which was his PhD thesis, and which basically, in one fell swoop, invented the idea of interactive CAD design and 3D modeling. And the key was that it was interactive. It wasn't, typing up a program that you fed as a bunch of punch cards to a big mainframe, and then a day later the result would come back, or typing in a program and then submitting it as electronically as a batch job and waiting till it's there in the queue. So he really had this idea that you were in this interactive loop coupled to the machine. And here is Alan. He's actually a Berkeley grad from EE in 1955. Not from computer science, because there was no computer science department in those days. And he worked at SRI, Stanford Research Institute in Menlo Park, on a project that was funded by ARPA, by this research agency. And he was really strongly influenced by Bush. His goal was to augment human intellect, just like Bush wanted to augment the power of scientists to make new discoveries. And so one way to look at his research is that in some ways he tried to build the MEMEX in 1963 that was described as a vision in 1945. Engelbart also won the Turing Award in 1997, and he is now, I think, in his late 80s, but at least until a couple years ago, he would still come to Berkeley about once a year to, give a brief address or come to some event that was of interest to him. So his major system was called NLS, the online system, and on Monday we saw a brief clip from that. And so the NLS was first demonstrated at the 1968 Fall Joint Computer Conference. It was the biggest meeting of computer scientists. It happened in San Francisco, and in this one demonstration, he introduced such a range of new techniques. He introduced word processing, email, functional hyperlinking, new input devices, and a whole range of other topics. So I'm just going to show you a short clip as well from this demo. I'm going to start this.
That way, we never did.
All right, so we're going to start with him explaining how his brand new input device, the mouse, worked.
Oh, see, standard, sometimes I apologize. It started that way, we never did change it.
He's apologizing for calling it the mouse.
If it moves up or down or sideways, so does the tracking spot. And the principles for its operation are quite easy to see. You'll turn it over, Don. Can you hear me, Don? Would you turn it over and we'll see, right? Its principle is that there are two wheels that roll on the surface. But since they're at right angles and kind of sharp edges, one roll and the other slide in one direction. Each of these wheels controls the potentiometer with the voltage output sampled by an ADV converter. The numbers taken in by the computer at sample times as to what the horizontal and vertical components are to be of where it should put the tracking spot. This device over here is unique to us, and we always have to justify and explain it. We'll do it in reverse order. We'll explain it first. It provides for you the one-hand equivalent of what you can do with a keyboard. There are 5 keys, and normally each finger sits on a key, and pressing any one key at a time produces a character. And any 2 keys at a time also. And in fact, any combination of depressing, of which there are 31 combinations. And one of their designers, John Kelly, came one day, spent a day working with us about our ideas about our control consoles as being separated from display consoles, and ended up making this on a chair that I could get up, move around, and sit down, and swivel, and rock, and lean back, and work. Very relaxing. I'd like now to have us bring in Jeff Wilson from Menlo Park. We'll switch to his console. He's sitting one just like this, and working independently. Hi, Jeff. We're not hearing you very well.
Oh, you're not hearing me? How about now?
That's fine. Okay. Programmers, you programmers are the ones who most intensely found use for working online as we're building up. Sort of how you structured your system guide. Okay?
All right, so there's a whole 90-minute video that you can easily find online, and it's a little lengthy, but there's so many gems sprinkled throughout that it's really worth your time to just look at the whole thing at some point. So just to point out, we talked about this when we talked about input devices, right? So one of the novelties here was this corded keyboard where they just mapped the letters of the alphabet to a 5-bit pattern. And so hitting multiple chords of keys would give you any letter in the alphabet, but you still had the other hand free for pointing at the same time. And here's just a close-up view of the first mouse, the very first one. So the very first one you can see was just hacked together out of a block of wood. And this mechanism from this engineering digitizer. All right, moving ahead. We're not quite yet at personal computing. So in the 70s, what was common were these hobbyist kits that were described in magazines like Popular Electronics, where you could build your own computer at home by just, soldering a couple hundred or 1,000 different components. And so actually the very first Apple computer, the Apple I, was part of this homebrew movement as well. So you would get the circuit board. However, you still had to add a case, a power supply, a keyboard, and a display. So technology was coming down in price, so interested hobbyists and amateurs would tinker with it in their garages, but it was certainly not at a package-complete level where you would just go to a store and buy one of these. That didn't really happen until the late 70s and early 80s, and really one of the main drivers of that was actually the spreadsheet. So the lowly spreadsheet was the killer application for personal computing that drove lots of people to see the value of spending a couple $1,000s on this machine. Because all kinds of business processes and even running your home budget required making tables and calculations and updating them. And the spreadsheet gave you this very flexible substrate for performing all of these different tasks. And so it really pulled in lots of people and convinced them to take the plunge. Now, the graphical user interface we think about today really had its origins in a research project at Xerox PARC. So this was Xerox's research lab. It still exists. It's down in Palo Alto in the hills behind Stanford. And the Xerox Star introduced ideas such as a bitmap display. So you're not just showing character blocks, but you have raster graphics for the display. Ideas like windows, icons, menus, a pointer. Notice how Engelbart still called it a tracking spot, because the word cursor hadn't been agreed upon yet. And this whole metaphor of what we learned about in terms of direct manipulation had its origins in this project. And so I'll show you one additional brief clip, also very poor quality because it's been transcoded from VHS, and who knows whether it even started on VHS. But of people at Xerox PARC explaining this user interface.
I'm David Smith. I'd like to introduce you to the Xerox 8010 STAR information system. This is a new computer designed for office professionals. It consists of a processor, a large display screen, a keyboard, and a pointing device called the mouse. STARs are normally connected together by the Ethernet local area network. This not only allows STARs to communicate with one another, but it also lets them share resources, such as file storage and printers. The mouse has a ball on the bottom that rotates as the mouse slides across a flat surface. This moves a cursor on the screen in corresponding motions. It has two buttons on top that can be sensed under program control. You can use these buttons to specify objects and destinations for commands. The keyboard consists of a standard typing array and three groups of function keys. The left group contains the generic functions: delete, copy, move, and show properties. These four are used throughout the system. For example, you use the same function key, move, to move a character in text, a line in an illustration, a fraction in an equation, or a document in a file drawer. The top group of keys consists of common text formatting functions, making text bold, italic, underlined, super or subscripted, or in a larger or smaller font. The right group of keys consists of miscellaneous functions for getting online assistance, defining and expanding abbreviations, stopping ongoing operations, and others. The display screen shows your working environment. We call this the desktop. It is an electronic analog for an office. On the screens are small pictures or icons representing familiar office objects.
So note, once again, the terminology had not been agreed upon, so he has to kind of explain and motivate why they picked these terms.
We call this selecting the object. Selected objects highlight in reverse video. You can then operate on the selection with the delete, copy, move keys, and other keys. Let me select some of the other icons on the desktop. This is a folder, a records file, a file drawer, 3270 and teletype terminals, printers, and in and out mail baskets. Using the move key, you can arrange your desktop in any way you like. Move is the most powerful command in the system. It replaces a large number of conventional computer commands, which we will point out as we go along. The copy command...
One thing to note here is that they made the conscious decision that there are operations that apply in any application, and then they just gave them hardware keys. Right? The equivalent to that, what we have now, is that there are conventions in each application that, for example, Control-C is copy and Control-V is paste. However, past these couple, the conventions quickly break down, and different applications do different things. And so by forcing the operations to actually have keys on the keyboard, there's no space for making the wrong decision in any particular application.
The moving, copying, deleting, and showing properties. You can open an icon to see what's inside. You do this by selecting the icon and pushing the Open key. The enlarged form is called a window. Every icon has its own window. This is a document window. displaying the contents of a document.
All right, so the other aspect that was fairly revolutionary here is that the documents were what you see is what you get. Right? So they weren't just an abstract representation of what a printed page would look like, but they were actually typeset in the right font size, etc. And that's where you can tell that Xerox was behind it, because their main business was selling printers and copiers. So the Star was revolutionary, but it never sold particularly well, partially because it was really expensive at $25,000 in like 1980 dollars. But then Steve Jobs visits PARC. So they had been working on their own small startup company making computers. And he sees the Alto, which was the research precursor to the Star. And then, curiously enough, a lot of these new design decisions that appeared in the Alto and the Star suddenly popped up in the Macintosh as well, or in the Macintosh precursor, the Lisa. And the Lisa in 1983 at $10,000 failed, but then the very next year, Apple introduced the Macintosh, which had a very similar windowing system, mouse-driven interface, icons, all of these abstractions you saw from Xerox, and really changed the personal computing market for good. All right, which brings us, so this is the history of computing from the astrolabe to the personal computer. And I thought I'll also just show you a quick history of how mobile computing came to be. So let me just switch my deck for that. So telephony was invented in the 1870s, and then this is the Model 500 telephone. We saw the industrial designer Henry Dreyfuss. Right? We saw some sketches for the human factors analysis for this particular phone. And this was what was in every home in the 1950s. At the same time, in the 1960s, that was what most computing still looked like. So this is the IBM 360 mainframe that was sold between 1964 and 1978. And so the question is, how do we get from here, from this version of talking to each other, and this version of computing, how do we get to this? And my main thesis here is that basically desktop computing approached mobile computing, and desktop phones approached mobile phones, and the two strands became ever closer until now, today, they're very tightly intertwined. All right. First mobile telephone was when? Any guesses?
1870.
It was not 1870. It took a while. It was in the 20th century. The 80s, okay. Who thinks 80s? Who thinks 90s? Later. Earlier than the 80s. 70s. 60s. 50s. Okay.
Car phone.
The earliest mobile phones were car phones. Why were they car phones? Because they were too big to carry around. It was basically the battery and the radio of it took up your entire trunk. But these existed so that, people of enough means could make important calls while on the road. Really, though, what we think of as mobile phones started with Martin Cooper at Motorola, who developed the Dynatac. So I think the first prototype existed in '73, and then it took another 10 years of development to get it into a consumer product that you could go out and buy. And then it took another 4 or 5 years for the phone to really break into public perception. And probably the movie that did more of that for that than anything else was Wall Street. So Michael Douglas, walking on the beach, talking on the Dynaphone brick. It's kind of an iconic moment of that time. And then pretty soon after that point, things really take off. So here's a chart of that Nokia made of all the phones, the models they sold between the early '80s, which were briefcase phones, and Dynatac-like phones, till the mid-2000s. And one thing you definitely note is this change of dominant form factors that happens over time. So you start with these large bricks, and then by the '90s, things had gotten small and miniaturized, and all phones looked like candy bars with a small screen in the middle. Right? And then took another couple of years till all of those candy bars and keypads disappeared. So when you think the first touchscreen phone was introduced to the market? I hear mid-90s. Other guesses? 80s. No, it took a little longer. The very first touchscreen phone was the IBM Simon. It was marketed in 1992. Launched at Comdex, a computer industry trade show in Las Vegas. It was sold by Bell South. It actually had some applications. So it had a calendar, an address book, a world clock, a calculator, notepad, email. You could also send and receive faxes. Which may sound funny, but because now that seems like obsolete technology. But until not very long ago, that was the main method of transmitting documents without mailing them. A standard had been agreed on how to send faxes, and this was a way of typing a message and sending it to someone who didn't have an email account but a fax machine. It also had a predictive keyboard and no physical buttons. And once again, it failed miserably in the marketplace. So there's this common story of technology being ahead of its time, right? And it's technologically feasible to build these devices, but you can't yet make a profit off of them. The first device that had this notion of being a communication center, not just a phone, that actually was successful was probably the Nokia Communicator from the mid-90s. Looks like a candy bar phone, but it was actually twice the size. And then flipped open along the middle and had a full QWERTY keyboard underneath and a second screen inside. So it was like a mini laptop plus phone in one. And that did fairly well. Another interesting place along the way was then the BlackBerry, which notably actually started without having any phone functions. So this really came more out of the success of the BlackBerry came out of the line of pagers that were, for example, used in hospitals for doctors. And so there were pagers where you could get paged, and then there were two-way pagers where you could also send a message back. And so the first really successful BlackBerry device was basically a two-way pager with a QWERTY keyboard that fit in your pocket. And voice was an afterthought. And then, of course, since then, you know, mobile computing has been one of the major technological drivers of change societally in general. And if you look at these graphs, even in 2007, the developing world was rapidly approaching one mobile phone per person. And we've eclipsed that as well. And if you look at the growth rates of personal computers versus personal phones in the developing world, both curves are growing, but the adoption curve for mobile technology is much, much steeper than that for personal computers. So for much of the world today, the only computer that people are familiar with is a mobile phone. And what is happening now is these used to be feature phones, so candy bar style phones, and now that prices have dropped enough, we're just about at the limit where you can buy unsubsidized smartphones that run an operating system and applications for about $100 in much of the world. All right, so that's the history of telephony. What about computing? Here's the very first mobile computer. The Osborne 1 was considered the first truly portable computer. It had about a 4-inch or so CRT. This was before LCD screens. And the whole thing was basically a suitcase. So the keyboard would be attached to the rest of the computer, and then it had a handle on the other side. There's very thoughtful storage slots for your floppy drives. There was a modem port, and then also its own set of, it ran its own operating systems with applications. Once again, a pioneer that was a failure in the market. The first really successful mobile computer came 2 years later, and that was the Compaq Portable. The history behind Compaq is interesting in that, this was founded by a bunch of engineers who left Texas Instruments and set out to produce a machine that was compatible with the IBM PC, IBM's personal computer that ran DOS. Now, there was this slight problem in that to get a working computer that was compatible, you actually had to have a BIOS that was compatible with IBM's BIOS. But IBM regarded that as a trade secret and kept it under wraps. And so Compaq was basically founded on a very successful example of reverse engineering, where Compaq had two different teams of engineers, one who would poke at IBM machines, trying to find out what the BIOS did, and then they would write down notes about what they found out, pass these notes to another team that would then implement, take that as a specification and implement something. So they kept the two groups apart, so they had an argument that they didn't actually infringe on IBM's intellectual property, and I believe that was held up in court, and Compaq was one of the most successful computing companies for a while. If you thought about the vision of what mobile computing looked like, it basically looked like that, right? The successful business executive could impress a stewardess by the very manly suitcase. That would probably then have to be checked anyways because it wouldn't fit under the seat or in the overhead bins. So miniaturization came soon enough, though. Here is the grid compass. The first laptop with a flat display. This was a transflective display. The industrial design of that was done by Bill Moggridge, who later co-founded IDEO which we've heard about a number of times in this course, and too expensive for most businesses or private users, but NASA had the funds, so this was the first laptop in space as well. Now, for consumers, though, what was more affordable were devices like these. So in the 80s, you could buy these small smart organizers that had, for example, managed your contacts, calendars, appointments, and indicative of this is the Scion organizer, which actually in the US was, I think, used at Marks and Spencer or another department store chain where all the employees had these to keep track of inventory. And you could program these. So these ran, I believe, a version of BASIC. But there were only 1 or 2 lines of text display, so not a very efficient interface. Another vision of mobile computing that was really influential was once again done at Xerox PARC. This is the PARC tab. So they had the vision of computing at different scales where you had the wall scale, where you had large displays or projectors, and then the pad scale, which is something that you could fit in your pocket. And so this was a mobile device that ran applications, and I guess the killer application there was email. And all of these were networked while you were on campus at PARC. And they were networked wirelessly. What you see sticking out here is an infrared transceiver. So there were infrared beacons built into the ceiling in each of the rooms of the lab. And there was an IR light sensor in here that would see the infrared beacons blinking, and then it would also have an IR LED that would blink, and the transceivers in the ceiling would have a sensor to exchange messages. It was also pen-driven. And it fit into this whole vision, right, that Mark Weiser articulated, which he called ubiquitous computing, that said that, well, really instead of us sitting down in front of a gray box on our desk, computing should become integrated into the fabric of our lives, and that means that there should be lots of different form factors that we may use over the course of a day. And so if you notice what we use now, our smartphones basically correspond to pads, our tablets correspond to their tabs, and then the one technology that hasn't taken off on the consumer level, where each person owns a device, is really this wall scale. However, this whole vision of ubiquitous computing was really influential, and there's a whole very respectable research conference that's just called Ubiquitous Computing, basically named after his vision. Part of this vision was also context awareness, so you would sense what people are doing. And back then, there was already this idea of having smart badges that tracked you, once again, through IR. And so you would know where people were in the building. You could exchange contact information just by running into each other, which seemed valuable, but also even then raised these questions of how much tracking do you actually need, and what are the downsides in terms of privacy and security. One of the great failures of mobile computing was the Newton that Apple released in 1993. So here the vision was, it's this intelligent personal assistant that helps you be more creative, and it would have handwriting recognition. And one reason for the failure, maybe Apple bit off too much at that point, but there was just not enough processing and battery available to do this reliably and fast enough to a level where people actually wanted to buy it. And the Newton failed badly enough that Apple basically backed out of the whole mobile computing market for a whole decade and only came back to it with the iPod and then later the iPhone. What was very successful, though, at that time was the Palm Pilot. So it did less than the Newton, but it did those fewer things much better. And so one of the insights of the Palm Pilot was, well, handwriting recognition is a really hard problem in general, and doing it on an underpowered mobile CPU is especially taxing. So why don't we do some co-adaptation where we'll try to recognize the handwriting, but also get people to provide input that's easier to recognize. And that's where the graffiti alphabet came from, where these strokes are much more distinct from each other than general handwriting. And by adopting these strokes, people became fairly proficient. It was fairly close to normal handwriting, so not too difficult to pick up, but the recognition accuracy was much higher. What's interesting, though, is that after that, so the Palm Pilot really established this market of having a personal digital assistant that would run applications with you at all times. The handwriting recognition and pen and stylus input kind of disappeared again. And so there's a good question of whether, again, technology wasn't quite right, or whether we actually don't value pen input all that much, because most of the things we may express may just be text, and for that, giving people a keyboard may just be more efficient. All right, that's the overview of the history of user interfaces in general and mobile computing in particular. On Monday, we're going to look more into the future, at future interactions, what research is doing at the moment. And then next week, Wednesday, we'll have our panel on mobile startups. And I believe we have 4 companies signed up for that right now who will be here for that. All right, see you next week.